gonna record and share screen with you. Can you see my slides? Okay, great. So last time we started talking about indices. So the idea is to speed up select statements or SQL queries, like this one, selecting star from student where name is equal to Alan Sam. If I don't have an index, I would have to search the whole table. Yeah, so this means reading a lot of blocks from the hard disk and moving them to the main memory. Okay, now it depends, of course, on whether the file is sorted on the field name physically on disk or not. If it's sorted physically on disk using name, I can do binary search, but most likely it wouldn't be sorted because sorting a big file or a big table is very expensive. So most likely will not be sorted, and I would have to do a linear search to find the record corresponding to Alan Sam. Okay. Then the idea was to build these auxiliary data structures or files called indices on top of a table. Yeah? And you can build as many of them as you want, right? Each one would be defined on a field or multiple fields. And these would help you speed up queries, search queries on this field. So for example, here we have an index on the field name, and that helps me speed up the searching operation when I'm looking for as an employee is a particular name. Why? Because the index file is much smaller in size and it's sorted. So I can do binary search on it, and I will do fewer number of block reads or transfer because the file itself, the index itself is small. It's much smaller in size. Yeah? So it fits, might even fit in main memory directly. Yeah. We looked at different types of indices. So we looked at primary indices, clustering indices, and secondary indices. I'll quickly remind you of the three. So a primary index is on a field that is a key. So the indexing field is a key, meaning it's unique, and the file is physically sorted on this field. And we said we can have only one primary index per table. Why? Because the file has to be physically sorted on this field. Okay, so this is how the primary index looks like. You have one entry per block. Yeah, so you're doing block anchoring. So you have one entry per block, which is typically the first record in the block. Yeah. And then we talk about clustering index. Again, the file is sorted physically on the indexing field. So here it's the department number, but it's not a key. So we could have repetitions. So this is how the clustering index would look like. Again, we would have one clustering index per table. We can't have multiple because the file is physically sorted on this field. And I can't sort the same file on multiple fields at the same time. Yeah? So store it physically on disk, right? In different in orders, ordering it based on department number and name at the same time. Yeah, you have to pick one of them. Okay. So in the clustering index, I have an entry per distinct value. So for all the employees with department 1, I have one entry. And then for all the employees with department 2, I have one entry, and so on. And the pointer, the block pointer, points to the first block that contains this value. That's what index. Right? I'm gonna mute all of you because there's some noise. Continue. Okay. Then we talked about secondary indices, and secondary indices can be defined on any table. So whether the table is physically sorted on disk or not, on any field, whether it's a key or not. Yeah. So they're the most flexible type of indices, and you can define multiple secondary indices per table. So you can define a secondary index on the field name, but you can also define a secondary index on the field department at the same time. Yeah. Okay. So it is an example, right? So this is an example of a secondary index on a key field, and you would have an entry per record. So every record, right, corresponds to an entry in this index. So 9 here, the record 9 here appears on the second block, the first entry in the second block of the index. And the block pointer points to the block that contains this record. What advantage does the secondary index give me? Again, it's sorted, so I can do binary search. And the size of the index is much smaller than the disk, the file. So I can do, right, I would do fewer number of blocks transfer. Okay. This is one example of a secondary index on a non-key field. So you have repetitions here. You see that one appears here and it appears here. And the table is not physically sorted on this field, department number. Yeah? So I'll create one entry per distinct value, and then have a pointer to a block of pointers which contains the record pointers to the various records that have this value. So this block has, you know, few pointers that point to this block and to this block and to this block, because all of them have records with value department number equal to 1. Okay. Today we're going to talk about multiple indices on multiple attributes. We're going to talk about multi-level indices and then how to create indices using SQL. All right. Any questions about the material from last time? Okay, good. So in many retrieval and update requests, multiple attributes are involved. What do I mean by this? I mean, in the select statement, you typically have AND conditions. So you want to select, right, star from the table employee, where name is equal to this, and, you know, let's say another field is equal to another value. So you would have conditions on multiple attributes at the same time. Yeah, that's what I mean by multiple attributes are involved. Yeah, this is very common. So if a certain combination of attributes is used frequently, you know that I use them frequently in my SQL queries. So I typically search by them, right? This combination of attributes, it might be beneficial or advantageous to set up an index on these, this combination of attributes. Yeah, so you can create basically an index on multiple attributes at the same time. Yeah, similar to the idea of composite key. You have a composite key which consists of multiple attributes. We would have a composite indexing field consisting of multiple base attributes. For example, let's take the table employee, assume that social security number is the primary key, and you have this set of attributes: age, street, city, zip code, salary, skill code, and department number. And we want to, usually we search for employees based on two fields, right? Age and department number. So we typically are looking for people who are in this department, whose age is greater than this value, or whose age is equal to this value, and so on. So I always want to, you know, find people based on department number and age at the same time. Yeah. So how do I efficiently process the query list? For example, list the employees in department number 4, whose age is 59. Okay. If there is an index on department number but not an age, I can use the index on department number. Yeah. If I don't have any indices, what do I have to do? I'd have to do linear search. So basically go through every record in the table and check whether it satisfies this condition, that the employee is in department number 4 and his age is 59. But if there is an index on department number only, I can use this index. So it will speed up the operations a little bit. How? So I can access the records having department number equal to 4 by doing binary search on the department number index, and then select among them. So that will give me all the employees in department number 4. And out of these, just do filtering in main memory. So once you have these in main memory, you filter out only anybody that is not that does not have an age equal to 59, and keep only those who satisfy age equal to 59. Yeah. So the idea is I'll read all the blocks of all employees in department number 4, and based on this, select the ones that have age equal to 59. Okay, so it's a speed up, a little bit of a speed up compared to doing linear search on the table. Let's see the other extreme. What if I have an index on age but not on department number? What would I do in this case? I would get the employees whose age is equal to 59, okay, using the index on age. that would give me all the employees whose age is equal to 59. These would be in multiple departments, of course. And out of them in main memory, as I'm reading them, as I'm transferring the blocks that satisfy age equal to 59, filter out anybody that is not in department 4. Yeah, that would give me the answer to my query, all the employees which are in department number 4 and has an age of 59. Okay. If I have an index on both department number and age, I can use both of them at the same time. So this is great, yeah? So both indices may be used. I can use the first index on department number to get all employees in department number 4, use the second index on age separately to get all employees whose age is equal to 59. So I have now 2 sets of employees, ones that are in department 4, one that are whose age is 59. How do I get the ones that satisfy both conditions? I do an intersection. So I do an intersection of the records retrieved from the first index with the records retrieved in the second index, and that would give me the record that satisfy both conditions. Okay. So what happens is when you run a query like this, select star from employee where department number equal to 4 and age is equal to 59. My SQL or any database management system would have to decide what is the most efficient way to access the data. Yeah. So it looks at what indices do you have in the database or on this table particularly, and based on this estimates what is the one that would result in the fewest number of blocks to be read. So it will estimate, right, if I use department number index, if I have one, how much blocks would it take to read, and then we'll estimate okay, if I use the age one, how much blocks would it have to read, and it does some estimation, and based on this decides what is the best route to execute this query. No, now if I have these 2 separate indices, one on department number and one on age, they might be that neither of them is efficient enough. In the case when you have a lot of records that meet each condition separately, so you have a lot of employees in department number 4, you have a lot of employees whose age is equal to 59, but the intersection is really small. So you have only, let's say, 4 employees who are in department number 4 and age equal to 59. Yeah. Let's see why this is inefficient, because, okay, I will do department number alone. So I will have to read maybe tens of blocks to get all the employees who are in department number 4. And then for age equal 59, I will also, let's say I have, thousands of employees that have age equal to 59, then I will have to read a lot of blocks to do this. Of course, it's more efficient because I'm using an index, but still I'm reading a lot of blocks because that's how the data is. And then out of all of these, right, I just need 1 block at most, or 4 blocks at most, because, right, I have only 4 records that satisfy this condition: department number equal to 4 and age equal to 59. Yeah. So in cases like this, it might be beneficial to create an index on both attributes at the same time. What do I mean by this? You can go in MySQL and say, I want to create an index on 2 attributes, department number and age at the same time, and in that order. That means what? That means that the indexing field, the first column in the index, would be actually the combination of these 2 attributes, department number and age. And you can do primary index on it, or a secondary index, or a clustering index, depending on, of course, whether this is unique or not, and whether the table is sorted on these 2 attributes at the same time or not. Yeah. So what's inside the index, how it's going to look like? It's going to be sorted like any other index. So basically all the keys with department number 1 would appear right before department number 2, and so on. So you have right sorted by department number first, and within departments, it's sorted by age. Yeah, default is ascendingly. So basically you would have all, all the records, right, or all the values, the entries in the index are sorted by the department number, and within one department, sorted by age. Okay. So this is how it would look like. Now I can use it to basically retrieve the records. So now if I have a query like find me all the employees who's in department number 4 and age equal to 59, I can use this composite index to get to these values. Basically, I will do binary search on DNO equal to 4 and age equal to 59 to identify the value, right, in the index that corresponds to this entry. And then out of this, just follow the pointer and read the blocks that have the record that satisfy both these conditions at the same time. Yeah? So it's an extension of the idea of an index, but to multiple attributes at the same time. Okay, we'll see how to do this in MySQL in a bit. Questions? Okay. Now we'll talk about multi-level indices, which is really the closest to what happens inside a database management system. So this is how indices are implemented most of the time in database management systems, yeah, as multi-level indices. What are these? So the idea is the following, right? So this was, I was asked about this the last time. So somebody asked, why can't we create a multi-level, right? An index on top of an index? Yes, we can do that, and we definitely do this in databases. So the idea is that since a single level index is an ordered file, so remember that, you know, when I create an index, it's an ordered file. It's physically sorted on this. Then I can create a primary index on top of it. So I can create an index to the index. And why primary index? Because the file is physically sorted on the indexing field. So I can create an index on top, a primary index on top of it. Okay. In that case, right, the original index file is called the first level index, and the index to the index is called the second level index. And then I repeat the same process. For the second level index, I create an index on top of it, a primary index. Primary index would be the smallest in size. Yeah, it's better than a secondary index because I can only include one entry per block, so it's not dense. And I can repeat this process over and over and over until the top level index fit in one disk block. Yeah. Note that this the idea of a multi-level index can be created on any type of first level index, as long as it has distinct values and fixed length entries. Yeah, it makes it easier to maintain. So let's see an example. Here's an example of an index with two levels. Question for you, what is the type of the first level index? Can you tell me? Is it a primary index? Is it a secondary index? Is it a clustering index? You should know. Look at the entries in the index and see what do they correspond to, and look at the key, right? The indexing field, is it a key or not? Based on these two things, you can answer whether it's a primary index or a secondary index or clustering.
It's primary.
It's a primary index, exactly. Why? Because I have an entry per block, yeah, typically the value of the first record, and the file is physically sorted on the field, and it's unique, it's a key. So this is obviously a primary index. And you see the primary index has, you know, only 4 blocks versus, right, the number of blocks for the table itself. Okay, so I have this end. Now I'm going to create a primary index on top of this first level index. So this is this one. So what is a primary index? You create an entry per block. So I have 2 here. I will have an entry for 2 here and a block pointer that points to this block. 35 and a pointer to this block. 55 and a pointer to this block, and 85 and a pointer to this block. And now this fits in one block, so I can stop. I don't have to create an index on top of this as well, because, right, the last block here, the last index or the top level index fits in one block, so I'm done. So the idea is I keep creating indices on top of each other, primary indices, until I reach one block. Okay. Searching, how do I find the record? Let's say I want to find the record 29 in the table. So select the asterisk where the, you know, the field is equal to 29. How do I do? I can do a search in the top level index. Yeah, so I read this block from the disk. It's one block. I read it from disk to memory. That's one block read, so it's not expensive. Do a binary search on this. That will tell me 29 is between 2 and 35. So I read 35, right? I go here. Correct? It's between 2 and, sorry, I read this. So I go here, and then I do a binary search here. It's between 24 and 35. So I follow the pointer of 24. That gets me to the record 29. So how many blocks do I have to read? I read this one, and this one. So 3 blocks in total. Yes, so the idea is I keep doing binary search on the top level index and then read a block corresponding to the right value, then do binary search on this block, or even linear search. It's a block in memory, so it's not expensive, and then follow the pointer to the next block, the next level, and so on. So in total, if I have T levels, if my index contains T levels, then I would do T plus T blocks. So I read T blocks, right, corresponding to these T levels, because I'm reading 1 block per index level, and then some additional blocks to retrieve the record. Why some additional blocks? Because I have to read the records themselves from the disk, from the table. And this depends on the first level index. If it's a primary index, then I would read 1 block only. But if it's a secondary index on non-key field, then I might read multiple blocks, because the records might be scattered across multiple blocks and on this. So it really depends on the first level index. How many blocks would I have to read? What about insertions and deletions? They're very expensive, because I'd have to maintain all of these indices. I have so many indices. So I could have 4 levels or 5 levels. These, I have to insert the record in the right position in the table, and then update the first level index, and that might entail updating the second level, third level, fourth level, and so on. So they're quite expensive. We'll talk about how. So basically this is why they're typically implemented as B trees or B plus trees. I'll show you a little bit what this means at the end of the lecture, but it's not part of the course. So we have additional slides on this. You can look at it if you know particularly data structures, or you've taken data structures, but it's not obligatory. So it's not. You're not gonna be asked about this in the exam. But to speed up the idea of searching and deletion, insertion and deletion, we typically use a data structure like B plus trees. Who knows red-black trees? Have you taken this in data structures? Anybody has taken data structure course? Yes, so it's very similar. Okay. Yes, so it's very similar to the red-black trees idea. It's nothing different. It's okay if you don't remember it, or if you haven't taken it, it's not mandatory. Just a side note. What I want you to know is that we use something like a data structure like a B plus tree to speed up insertion and deletion. I'll show you how in a bit. Okay, let's do an exercise. Let's see. It's a very important exercise. So let's go through it together in details to see how does a multi-level index speed up searching operations in databases. So we're gonna assume we have we wanna create a multi-level index on a file, on a table, which has 30,000 records. The first level index is a secondary index on a key, okay? What does it mean, a secondary index on a key? It means that the file is not physically sorted on this field, So basically the records could appear in any order on disk. So basically you could have the first block contains records with value greater than the records in the second, and within a block they're not even sorted. So it's really the file is scattered across multiple blocks in any order. Okay. So the indexing field size is 9 bytes. So I know that the key is 9 bytes and the block pointer is 6 bytes. And the block size is as before 1024 bytes. Okay, so let's compute how many levels do I need to really reach, to create this multi-level index. That's the exercise we wanna achieve. Okay, so the index entry size is again just the value, the size of the value, the indexing field, plus the pointer, the block pointer size. So it's 15 bytes. The index blocking factor is the size of the block divided by the size of the index entry. So how many entries fit within one block? We've done this before. That's the floor of 1024 by 15. That's 68 entries per block. So I can fit 68 entries per block. for the first level index. Yeah. So how many blocks do I need for the first level index? It's easy. Yeah. So all I have to do is say, okay, how many entries do I have in the first level index? Since it's a secondary index on a key, this means I have an entry per record. Yeah. So I would have 30,000 entries. I have 68 entries per block. So how many blocks do I need? I need the ceiling of 30,000 by 68. Yeah, that gives me 442 blocks. So the index, in order for me to store it completely on disk, I would need just 442 blocks, yeah? Based on the fact that the first level index is a secondary index on a key. Okay. So I have 442 blocks. This means I cannot stop. I have to create a second level index on top of this index. Okay. So what is the total number of second level entries? I have 442 blocks. That's the first level index. Now the second level index is going to be a primary index. Why primary index? Because the file is physically sorted. So the index itself is physically sorted on disk and it's unique. Yeah, the value is unique. The values in all indices, the values are unique. We assume that. Okay, so I can create a primary index on top of it. So primary index means there is an entry per block. So how many entries in the second level index? It's equal to the number of blocks for the first level index, which is 442. So I have 442 entries. Okay. So how many blocks would I need if I have 442 entries? I know the blocking factor, I've already calculated it. It's 68. If I do ceiling of 442 by 68, I get 7 blocks. So the second level index is a huge improvement. 7 blocks only to store it, because I'm using a primary index. So its size is going to be much smaller than the first level index. So I only need 7 blocks. Can I stop now? The answer is no. I only stop when I have 1 block. So I'll create an index on top of the second level index. What type of index? A primary index. Yeah. So basically, I create a primary index on top of this second level index with 7 blocks. Okay. So let's see total number of third level entries. How many entries? If it's a primary index and I have 7 blocks for the level before. How many entries? 7, right? So I have 7 entries because there is an entry per block. Remember, it's a primary index. So I have 7 entries. So how many blocks would I need for these 7 entries? If a block fits 68 entries, then I just need 1 block. Okay. So the third level index would contain 1 block only, and I can stop now because I have now an index that fit in 1 block. So how many levels in total would I have? I would have 3 levels. Yeah, 1 for the first level like index, 1 for the second level, and then 1 for the third level. Yeah? So I have 3 levels of indices, a multi-level index with 3 levels. How many blocks would I have to read to reach a record, any record in the table? Yeah, so any select statement that I type, how many blocks would I have to read? I'm at 4, exactly 4. Yeah, why? I would read the first level, the top level block. So the index of the top level is just 1 block, so I would read it, and then out of it we'll pick the block to read from the next level, and then a block to read from the next level, and then 1 block from the table itself. So in total, 4 block accesses versus, right, how many, I would have done linear search on the table if I didn't have this type of index. Yeah, or I would have done binary search on 442 blocks if I had only the primary, the secondary index, first level index, without this multi-level indices. So a huge improvement in performance because of this idea of multi-level indices. Okay, this exercise is clear. This is important. Yeah, we expect something similar in the exam. Questions? Any questions on this? So I encourage you to work out this exercise. I'll show you at the end some practice exercises that are posted on Moodle that I strongly recommend that you also attempt. Yeah, it's just one big exercise with multiple parts, and it's really important that you attempt this on your own. Questions? Okay. I'll stop here the meeting and then resume it again and continue with the last part. We will finish early today. Okay. Stop share. Stop record.